Good day, everyone. Welcome to the second lesson of our module. In the previous discussion, we now understand or we have experienced how to determine the probability of an event, especially in the definition that the probability of the event is equal to the number of outcomes for that event divided by the number of all possible outcomes, which is also the number of possible outcomes in the sample space. So that's the lowercase n divided by the uppercase n. Today we will be discussing one of the rules in probability, specifically the additive rules of probability. Now, in the additive rules of probability, we will calculate the probability of the union of the events. If you have two or more events, we can get the probability of those events, the combined probability of the events by getting the probability of their union. And we have several definitions for those or theorems for those. This is the first one, that the probability of two events, the union of two events, the probability of the union of two events rather, is equal to the probability of the first event plus the probability of the second event subtracted by the probability of the intersection of those events. Okay, and we know that the probability of the sample space is equal to 1. If the next definition or theorem we have, if A and B are two events and they are mutually exclusive, when we say mutually exclusive, they don't have an intersection. Okay, so mutually exclusive events uh, are events which don't have intersections. So their probability is just equal to the sum of those probabilities. So if we will show them in a Venn diagram, so you have A and B. So they don't have common outcomes or common values. Now, if more than one or more than two events are mutually exclusive, then their probability is just equal to the sum of each of the probabilities. And if the if more than two events are partition of sample space, then if we sum all of the probabilities of the events, that will be just equal to the probability of the sample space. We also have this definition for three events. As you can see here, their probability or the probability of their union is just equal to the sum of each of the probabilities of the events minus um, the probability of the intersections of uh, each of the pairs plus the probability of the intersection of the three. So if say for example, I have here three events. Okay, sorry for the. So we have A, B, and C, and this will be our sample space. Okay, the first thing to do is to get the probability of each. Okay, the probability of each event will be these inside these circles. Okay, this is P of A, P of B, and P of C, subtracted by the intersections, the probability of the intersection of each pair. So these are, you have the intersection of A and B, this one. We can say this is the intersection of A and B. This is the intersection of B and C here, and the intersection of A and C. Now, another thing is those intersections have another intersection, so which means we will add this one, this Oh, what happened? Okay, this means we will add this intersection here. This is the intersection of the three events, the A, B, and C. Okay, let's take this example. We have John is going to graduate from a civil engineering department in a university by the end of the semester. By the way, these problems were taken from our reference from our book, from uh, which is actually from the book, which is actually presented or shown in the module summary. So you can find, if you have a copy of that book, so you can find the different problems there. Okay, going back, John is going to graduate from a civil engineering department in a university by the end of the semester. After being interviewed at the two companies he likes, he assesses that his probability of getting an offer from company A is zero point 0.8 and his probability of getting an offer from company B is zero point 0.6. If he believes that the probability he will get offers from both companies A and B is zero point 0.5, then what will be the probability that he will get at least one offer from these two companies? So I am now highlighting the events that we might need. Okay, we have here company A, so we'll denote P of A or probability of A. Now for company A is zero point 0.8. Now the probability that company B will provide an offer to John is zero point 0.6. Okay, then which means we have here he believes that the probability will get offers from both, meaning from both A and B. Then we can assume that's um, the probability of the intersection of A and B. Okay, the probability of the intersection of A and B is equal to zero point 0.5. If you're going to show this in a Venn diagram, so the problem might look like this. You have a sample space, event A 0.8, then event B, that's zero point 0.6, so probably the size. Sorry about that. Okay, anyways, this is A and this is B. A has zero point 0.8 probability to give offer. B has zero point 0.6 probability to give an offer. And the area in between is zero point 0.5. And this is the intersection of A and B. So these are the given values in our problem. Therefore, what is asked is the probability that he will get an offer from both companies, which means the union of the two. Now, we cannot directly add zero point 0.8 and zero point 0.6 that would exceed 1. No, we know that the probability, you have to take note that the probability of the sample space is just equal to or is equal to 1. So therefore, following the given theorems, since there are only two events given, so that would be, oh, okay, there's no solution shown. So I will be just showing the solution. So that would be the probability of the union of A and B based on the given theorem is the probability of A plus the probability of B minus the probability of the intersection of A and B. And that's zero point 0.8 plus zero point 0.6 minus zero point 0.5. 0.8 plus 0.6 is 1.4 minus 0.5, that's 0.9. So I can therefore we can say, or Jen can say, that there is 90% probability that uh, companies B either companies B and A will offer, will give an offer. So that's 0.9 or 0.90. So again, this is how we solve for problems using the additive rules. Let's take another example. So what is the probability of getting a total of 7 or 11 when a pair of fair dice is tossed? Now take note of this term fair dice. Commonly, this will be presented or given in the problem just to denote that each of the numbers in a die has equal probabilities or equal chances of occurring. Now, here in the problem, there are two dice, no? Since we have a pair of fair dice, and we know that for each die, we have six possible outcomes. That's one, two, three. No, we have one, two, three, four, five, and six. Okay, there are six possible outcomes. However, since we have two dice, and based on our previous discussion in counting sample points, now we have how many possible outcomes can we get from tossing a pair of dice? That is actually 6 times 6, and that's 36. So therefore, for this um, for this problem, there are 36 possible outcomes. Okay, and that is the number of, okay, for a while. That 36 possible outcomes is the number of outcomes in our sample space. Okay, that's 36. So the probability of our S, which is equal to, uh, if we will get the probability, so that should be equal to 1. So that is based on our theorem, right? If you recall our theorems. Now, since there are 36 possible outcomes, if we will use a tree diagram, so please just let me use a tree diagram for presentation purposes. Now, each one, after the first die can have uh, six possible outcomes, and the second die can also have another six possible outcomes, which is a one can have a pair of one, two, three, four, five, and six. Now same with here, one, two, three, four, five, and six. Until six, we have six, one, six, two, six, three, six, four, six, five, six, six. Now here in the problem, we are only concerned with the outcomes, which has a total of 7 and a total of 11. So if we will denote A to be the event wherein the outcomes is a pair wherein the total is equal to 7. Now, what pairs, no, which has an outcome a total of 7? So if we will take a look at this tree diagram, we have 1 and 6. No, the result is 7. For 2, we can have 2 and 4, 2 and 5 rather, right? No, because that's 7. For 3, we can have 3 and 4. And 3 plus 6 is 9, so we don't have. Then for 4, we have 3. So the result will be 7. For 5, we can have 2. So result is 7. And for 6, we have 1. So the possible pairs that we can get are 1, 6, 2, 5, 3, 4. We also have 4, 3, and 5, 2, and also 6, 1. Okay. Now, what is the probability of getting an A? If we are asked, what is the probability of getting an A? So we know here that this is a fair, no, a pair of fair dice. Okay. So we have each of which here in the first die, each has 1 over 6 weight. No, each of these has 1 over 6 probability that the number will occur. Same with the second in the second die. We have also 1 6. So therefore, that's 1 6 times 1 6. Each of the combinations here, the possible outcomes for tossing a pair of fair dice has 1 over 36 weight or probability. Now, if we count, we have 1, 2, 3, 4, 5, 6. So adding all of them, we have 1 over 36. We can just have multiply it by 6 or simply adding them one by one. Okay, that's 1 plus 36, 1 over 36 rather, plus 1 over 36 plus 1 over 36 plus 1 over 36. And adding them up, since they have the same numerators, so the result will be 6 over 36. Okay, now that's the probability of getting 7. We are also asked of the probability of getting 11. Now, what are the combinations wherein the total, when we add the outcomes of the two dice, the total value is 11. Now, for 3 plus 6, that's 9. So it's not, we don't have 11. 4 plus 6 is 10. So which means the 11 can be found here. We'll have, uh, for 11, we have 5 plus 6, right? And 6 plus 5. So we'll have an 11. So there are only two possible combinations whose result is equal to 11. And these are again 5, 6 and 6, 5. Take note that I am using parentheses, so meaning these are ordered pairs. No, ordered pairs meaning they cannot be interchanged. Okay, so if you write 6 here, then 5 here, that's a different uh, pair. So which means, since we know that each outcomes has a weight of 1 over 36 and we only have two possible outcomes, that means the probability of getting these two is 2 over 36. Going back to our definition, we have the probability of the union of two events is equal to the probability of A plus the probability of B plus the probability of the intersection of the two events. Now the question here is, do A and B have common values? Do they have intersection? If you would take a look at the combinations, no, or the ordered pairs, they don't share the same values or shapes. They don't share the same ordered pairs, which means this is zero, and this would just tell us that events A and B are actually mutually exclusive, meaning they don't share the same elements. Okay, they don't share the same outcomes. So the intersection is zero. So what remains are the probabilities of A and B. And that's 6 over 36 plus 2 over 36. As you can see, I did not simplify the fraction yet. That is because I know that I will be adding these two. So that when I add these two, I don't have problems in the denominator. Now, if we recall, we can only add factor, fractions rather, we can only add fractions which have the same denominators. So I did not change the denominator so that I can easily add them, and this would result to 8 over 36. And this will be the time that we can simplify them, getting the common factors of 8 and 36. So what are the factors of 8 that can be divided by, that can also be divided to 36? And we have 8 is 8 times 2. 36 can be divided, 8 rather is 4 times 2, and 36 can be divided by 4. So we'll have 8 divided by 4 is 2. 36 divided by 4 is 9. So the probability of getting either 7 or 11, no, getting a pair whose total is 7 or 11 is 2 over 9. Or if we round this, or if we get the exact value of this one, we'll get 0, sorry, 0.2, 2, and 2. So this will be our final answer. So this is how we use the additive rules in probability. Let's take the other examples. Okay, let's have problem number 8. If the probabilities are respectively 0.9, 0.15, okay, 0.9 again, 0.15, 0.21, and 0.23, that a person purchasing a new automobile will choose a color green, white, red, or blue. So we have here, based on the given, we have green, white, red, or blue. So we have to write here. So the probability, let's use G to denote event. Uh, the selected automobile is green and it has a probability of 0.9. For selecting white, we have a 0.15 probability. For selecting red, there's 0.21 or 0.21 probability. And selecting a blue car or automobile is 0.23. If we sum them up, the result is not actually equal to um, 1. Now, this would mean that the customer might, the person might, there is a probability that the person would not buy or would select other colors. So if we'll get the total of these probabilities, we'll have, I think this is 8, 10, 8, so carry 1, we have 68. So the total probability of the union of these sets, or of these events. Okay, so I think that's problem A. Okay, we'll just show the solution here. So what's the probability that a given buyer will purchase a new automobile that comes in one of those colors? So we'll get the probability of these, that the buyer or the person will select any, so any of these colors, no, automobile colors. So that's the probability of getting green with the probability of getting white, red, and blue. So we'll just add all of them. So the 0.09 plus 0.15 plus 0.21 plus 0.23. So again, since we had already summed it up earlier, so the result is 0.68. Therefore, the probability of getting any of the probability that a buyer or a person will get any of these colors, green, white, red, and blue, is 0.68. Now we have another problem here. Another question is, what is the probability that the given buyer will purchase a new automobile that is not green? Okay, now uh, there is This one is related to this one will be related to the next topic, no, to the next discussion that's actually in the complement, but we will just show the solution here. So we will not choose green. Now, since this is the statement and it is not stated that he will buy any of these colors but not green, so it might be a different case. But since the statement is written in this way, or yeah, expressed in this way, so which means that we will consider the probability wherein there the the buyer or the person will not buy. Okay, so as you can see here, now we have 0.68. Okay, if you remember that the probability of the sample space is equal to 1. Therefore, if we will use if you will just denote O, okay, to be the probability of that the it's either the probability that you will not buy any of these colors, so that would be 1 minus 0.68, that is 0.32, right? So that's 1 minus 0.68. So, diba? If you recall that the probability of all the mutually exclusive events until A to N, yeah, if you recall the previous theorems, no, A to N is just equal to the probability of the sample space, and that is equal to 1. So that means the probability of getting green, white, red, blue, and others is equal to 1. So since we have 0.68 for the sum of the probabilities of these four colors, then the remaining will be 0.32. Here is the problem. Second problem, it says that the um, the automobile that the buyer will not buy a green one. So since the probability of selecting green is 0.9, 0.9, which means the probability that he will not buy a green, so let's say we will denote not, no, as a complement, is actually equal to just 1 minus the probability of getting or buying green. And that is 1 minus 0.09, and that is equal to 0.91. So that's the probability that you will not choose green. Again, as I've told you earlier that uh, the statement, no, it depends on the statement. Now, what if, let's have a C, now a problem C. What if the statement would just say that, what is the probability that the buyer will not buy a green automobile, but any of the remaining three? Meaning, what is the probability that the buyer will not buy green, but w- it can be white, red, or blue. No, we will buy any of the colors green, white, red, blue, but not green. So we can have just 0.68 minus 0. No, that will be just, we can just say, no, that's 0.68 minus 0.09, which is equal to um, that's 59. Okay, that's 0.59. Or we can just add the probabilities of these three, green, white, and red. So that's zero. No, rather, not we do not include green, but other colors. That's white, red, and blue. So 0.15 plus 0.21 plus 0.23 is 0.59. Okay, now you have to take note or be careful with how the statements were being written. So again, I have told you that the B here is actually um, presented in the next slide, and this is about complementary events. We have, if you have an event, of course, we have in a set, no, in the universal set, say for example, you have set A or event A. Now, those outcomes which are not part of A are the complement of A. So this one here are actually the complement of A. And if we add the probabilities of the two, the result is 1. So this is just the same with the probability of our sample space. So the probability of the event added by the probability of its complement is just equal to the probability of the sample space, which is equal to 1. Here are some additional problems. We have, if the probabilities of an automobile mechanic will service 3, 4, 5, 6, 7, 8 or more cars on any given workday are respectively 0.12. So we'll have here probability of getting 3 is 0.12. The probability of getting 4 is 0.19. The probability of getting 5 is 0.28. The probability of getting 6 is 0.24. The probability of getting 7 is 0.10. The probability of getting 8 or more, which means greater than 7, is 0.07. Now let's try to sum them up. So the probability of all of these, we have 0.12, 0.19 is 31 plus 0.28, um, it's 0.12, okay. 31 plus 59 plus this is 0. Okay. Say okay, 11, 19, 23 and 30. So this is 0, 5, 6, 7, 8, 9, 10. 0. So carry 1, 1.0. Therefore, in this problem, so this is now the union of all of these. So I'll just use S, no, since it has a probability which is equal to 1. So I will denote S. So therefore, in this problem, yeah, the mechanic will always have to service 3 or more automobiles. Now, meaning every day, every work day, the mechanic will have cars to be serviced. So that's the probability for sample space. Now, the question here is, what is the probability that he will service at least 5 cars on his next day at work? So you have here at least. When we say at least, meaning the minimum number of cars that he will service is 5. So that's probably these, right? You have, uh, there are many possible ways that we can solve for this. So if we get the probability of getting at least 5 greater than or equal to 5, we can just say 1 minus the probability of getting 3 and 4, right? Since uh, these two are not uh, included. So that's 1 plus 0.12 plus 0.19. And this is equal to 0.69. So 0.19 plus 0.12 is 0.31. So that's the probability of getting at least 5 cars. We can also just add, so this is the rule of complement, or we can also just add we can just add this 3. So the result would be still 0.69. Okay, so that's how we use the complement, the rules. This will be our last example for this session. So we have suppose that a manufacturer's specification for the length of a certain type of computer are 2000 plus and minus 10 mm. This one here is called tolerance, meaning the common outputs, okay, the common specifications or lengths of a certain computer cable can range from 2000 plus 10, that's 2000 minus 10 mm until 2000 plus 10 mm. So it ranges from 1990 until 2010 mm. So this is the specification, no? Meaning the standard cable will have these measurements. It's from within 1990 to 2010. Now, in this industry, it is known that small cable is just likely to be defective, not meeting specification as large cable. So this means that the probability of getting defective, getting a smaller cable compared to the specification has the same probability of getting a larger cable compared to this specification. So that is the probability of randomly producing a cable with length exceeding 2010 millimeters is equal to the probability of producing cable with length smaller than 1990. Now, if the probability that the production procedure meets within the specification is known to be 0.99. So let's use letters to represent the events. Now, let's say that if getting standard value or standard measurement, the probability is 0.99. Okay, so which means then we will use probably B. We will use B to denote for less than 1990 mm. Okay, and we will use the probability of C when producing greater than the maximum, which is 2010 millimeters. Again, remember these. So let's answer the first problem. So we know that again, the probability of getting A is 0.99. Okay. Then what is the probability that the selected cable is randomly too large? Now, we have there probability of B is for the smaller one, right? And the probability of C is for the larger one. So that's greater than 2010. But we don't know these probabilities. So therefore, we have to get first, what is the probability of getting both? We know this. Now this is just equal to the probability of A. Okay? And the probability of A is just equal to 1 minus the complement of A rather. That's just 1 minus the probability of A. And that is 1 minus 0.99. Then we'll get 0.01. Okay, so that's the probability of getting either B or C. No, getting a cable cable length which exceeds um, which is not within this specification. Now, since we know that the probability of, based on the problem, the probability of B is just equal to the probability of C, then we can just divide this probability. So that's equal to 0.01 divided by 2. And that's 0.005. So therefore, the probability of getting a cable which is larger or longer than 2010 millimeters is 0.005, or that's 0.5%. Okay, and then we have here problem B. So what is the probability that a randomly selected cable is larger than 1990 mm? We know that the probability of getting 1900 less than 1900 millimeters is 0.005, right? So it says that greater than or larger than, so which means we will get, this includes 1990, so on. No, 2010 millimeters and larger um, lens. So therefore, this would tell us that the one that we are looking for is actually the complement of B, and that's just 1 minus the probability of B. We know that the probability of B is 0.005. So that is 1 minus. So the probability of getting cables which has longer than 1990 millimeters is 0.995, or 99.5%. So that's how we use the different additive rules. Now, for your engage, I have here a problem. According to a Consumer Digest in July and August 1996, the probable location of personal computers in the home is as follows. A personal computer has zero point 0.3 probability that it's in the adult bedroom, 0.15 in the child bedroom, 0.14 in other bedrooms, probably in the guest bedroom or others, 0.40 in an office or a den. No, it's a separate room, and 0.28 probability that it's in other rooms. Okay, probably in the dining room or in the living room and other rooms. Okay, so that's the probability. Now you have there three questions with the answer. You'll just have to provide the explanation or solution of these answers. Okay, what is the probability that a personal computer is in a bedroom? So that's 0.32. Not in a bedroom, 0.68. And when you go to the house, well, which do you think will a personal computer is located? So the answer is office or den. So again, you provide the solution to this one. Letter C might you might be you might use sentences to prove, no, or to explain your answer. Okay, so this would be all for this session. Now, thank you for watching, and see you in see you in see you in the next discussion.